Hello, everyone, and welcome. My name is Celeste Straub, and I will be your host for today's webinar. This webinar is brought to you by the Critical Materials Innovation Hub, and today's topic focuses on lithium recovery, and this is going to be presented by T2M Global. First, a few logistics on today's webinar series. It is a webinar series hosted by Colorado School of Mines. If you have any suggestions for future webinars, please feel free to email and share those with us at cmi@mines.edu, or you can include those in your exit survey at the end of this webinar. This is a public webinar, and our recordings will be made available in about a week. They can be found at our website, aimslab.gov/CMI, and also on our YouTube channel, Critical Materials Innovation Hub. As our presenters share today, if you have any questions, please feel free to include those in our Q&A box so that we can address those at the end of our presentation. I encourage you to add those early so that we can have them already queued and ready to go. But before I hand it off to our two presenters, I would like to introduce them briefly. First, we have Pinakin. He is the president and co-founder of T2M Global. He holds a master's degree in chemical engineering and is an award-winning expert in fuel cells, hydrogen, and waste to value. Joining him is Ludwig Lipp. Ludwig is the VP and co-founder of T2M Global. He is an expert in waste to energy, hydrogen, and fuel cells as well. And with that, I'd like to hand it over to Pinakin and Ludwig to share their presentation.
Well, thank you, Celeste, for the kind introduction. We're honored to have been invited to present in this forum, and we want to thank all the organizers for this shared topic. To audience for taking the time to attend. We look forward to any questions you may have. Our present that our team has developed, which I will present, and followed by an overview of lithium extraction pathways and how the value proposition of direct lithium extraction can be enhanced using available waste heat, which Pinakin will explain. So T2M stands for technology to market. Our goal is not only to develop new technologies, but to commercialize them. Our mission is to create higher value from wasted resources. And I'd like to highlight 5 enabler technologies in our portfolio that all involve benefiting from stranded resources. First, a novel waste heat-driven cycle, which I'll explain in a few minutes, and Pinakin will show you how it can be applied to concentrating and extracting lithium and other valuable minerals. Second, a new technology to cost-effectively recover low-level waste heat, which we call super economizer. And so we'll focus on these 2 today, and the other 3 technologies shown in the black bullets are complementary and may be integrated in an overall mineral concentration system. So we're very grateful to our sponsors, and on the right-hand side, you can see Pinakin receiving an award from the CleanTech Open Startup Accelerator for first prize in the energy category. So we have a strong team with over 300 years of combined experience in new energy technology development. We're very fortunate to have an excellent advisory board with prominent advisors, including professors and former managers from DOE, CEC, and utility companies. And we have a good balance of public-private partnerships and university partnerships. I'd like to point out that combined heat and power is very important for lithium extraction. Bob Gemmer here is shown in the slide here. He's a lifetime achievement awardee from the National CHP Association. So waste to value technologies that we call WTV for short, they support the circular economy. Specifically, we focus on using them to increase manufacturing competitiveness in an environmentally sustainable fashion. And we do this using what we call an R3 approach for WTV technology. So recover, recycle, and reuse. And I'll highlight a few examples of WTV technology in the next few slides. So in the case of trigeneration technology, human waste is converted to biogas in an anaerobic digester, and then a fuel cell extracts hydrogen from the biogas and converts it to electricity at high efficiency. And the fuel cell also co-produces high temperature heat, which can be used to produce steam for manufacturing processes. And the third product in co-product in trigeneration is renewable hydrogen, which is extracted from the fuel cell exhaust. And that hydrogen can be used to power fuel cell cars and trucks, or as a chemical in petrochemical plants. And Pinakin led the development of this new technology, which, what you see here on the top left is a first of a kind in the world unit. And it was demonstrated for multiple years in California. And then Toyota picked up on the idea and supported a 10 times scale up at the Port of Long Beach in Los Angeles, which you can see on the right side. And that plant has a net power output of 2.3 megawatts. It co-produces 1,200 kilograms per day of clean hydrogen for the vehicles you see there that are in service at the port or that are coming in from ships. And it also co-produces 1,400 gallons of fresh water every day. So Toyota benefits from the lower cost hydrogen made on-site, and the port loves the support that the fuel cell provides to the local grid. And here you can see Pinakin receiving an award from DOE for his leadership in the development and scale-up of Trigen technology. Another technology we have developed to balance the grid makes use of wood waste, mostly from wildfire prevention efforts and forest management activities. And this can pile up in huge quantities in wood yards, as you can see in the left here. And that gets converted to green syngas in a novel biomass gasifier. And using excess electricity, T2M's proton pump then converts the syngas into renewable natural gas and clean hydrogen. And that can either be used in a refinery here or converted to high efficiency stationary fuel cells to provide demand response for EV charging, microgrids, or for on-site power. And we believe that this technology could be very useful in remote areas such as critical materials mines that don't have a grid connection. So the next 5 slides focus on low temperature waste heat, how we can recover it cost effectively, and what we can do with it. So out of 100 quads of energy used in the US every year, about 25% is lost as low-grade waste heat. And that corresponds to a $200 billion lost opportunity. And if that low temperature waste heat could be recovered and used, it could really lower operating costs and increase US manufacturing competitiveness. It's one of the largest untapped opportunities. And all that is because conventional economizer technology is too expensive. So that's why our team has developed super economizer technology, which has multiple advantages. First is the higher efficiency. It recovers a lot more heat. It's more compact, which is great for retrofits, as you can see on the right here, squeezed behind a process tank in a manufacturing plant. And it's also much lighter, as you can see here, being held, without effort, whereas corresponding conventional economizer would be way too heavy to lift. And it's also much lower cost. And that means the return on investment can be as short as 1 to 2 years compared to 5 to 15 for conventional economizers. And an important feature for lithium extraction is that it has much better resistance to corrosion and fouling. And Pinakin will elaborate on that later. So very useful for critical materials. Now, this table shows data from the 25 kilowatt super economizer testing. You can see heat exchange effectiveness is more than 80%, which is about twice that of conventional heat exchangers. And we have multiples of these in operation at a manufacturing site for now well over 10,000 hours, and we're observing stable performance. So what can we do with 60 to 80 degrees C heat, you may ask? And it can be used for process improvement or power production. So here we show the power production. Current commercial cycles, such as Rankine, Carnot, and so on, they're not cost effective for low-level waste heat. They use reciprocating engines or steam turbines. And we have developed a novel cycle that we call Pinakin cycle to convert this low-level waste heat to clean power. So it uses a novel membrane, which then pressurizes a fluid which goes to a water turbine. So that's very well proven technology and lower cost than steam turbines and very reliable. And now here the waste heat comes in with the super economizer that's used to separate the fluids again, and they go around in a loop. So there are no emissions of this whole cycle. We've demonstrated it at 5 kilowatt level and now scaling up to 25 kilowatt. And then this picture shows the Hoover Dam up here, which is one of the tallest in the US. And the bar chart here shows the dam equivalent height of Pinakin cycle. It's about 4 times higher pressure buildup in our novel membrane module compared to the height of the dam. And so it allows you to provide power without actually building a dam. And so that's why we call it a miniaturized hydropower plant. So with this overview, I now pass it on to Pinakin to tell you more about lithium extraction and how our technologies can make a difference there. Thank you.
Thank you, Ludwig. All these technologies we call WTV, waste to value, and lithium production is becoming very important. As you can see here, America is probably a major consumer of lithium-based materials, batteries, and other uses. But if you look at it, it's less than 1% of lithium is produced. Practically 100% of lithium we are importing, mostly from eastern part of the world, China, Australia, and some from South America, Chile, for example. And also, if you look at it, the brine evaporation technology and hard rock are the major part. DLE, direct lithium extraction, which is part of what I want to talk about. So I want to talk about 2 things. How can USA go from less than 1% to a major producer, and also bring the cost down sizably? So these are the market related data from Goldman Sachs and some other. They have forecasted, they are measuring in LCE, lithium carbonate equivalent, and projection starts 5 years ago, and then projects additional 5 years. And as you can see, the top 3 players, China, Argentina, Australia, are showing pretty good progress. and other countries are picking up. Looks like Africa may be a significant player, particularly China's investment there is going to be really not Africa, but Chinese technology. So that's another driving force for America to establish its innovation leadership. And these opportunities are very important, and I'll put an effort to explain some of these opportunities. Critical mineral resources, there has been quite a bit of studies. This is a geological survey, and you can see different minerals by color coding. They are explained on the right side, but at a high level, Checker Pass in Nevada, Salton Sea, California, and Salt Lake, Utah are low-hanging fruits. There are quite a few startup companies in this space that are looking actively, particularly California State is very active. Okay. And basically creating value from these untapped resources. Market dynamics, lithium feedstock sources are not single, they are diverse. And you can see left-hand side what we have now. Our majority of that is the hard rock extraction, brine, conventional, and then emerging DLE technology. And that circle is going to grow 4 times bigger in next 5 to 10 years. And it will have newer method, newer technology. What we are going to show is how the DLE will play a bigger role. The traditional lithium extraction is like very, very extended time. It takes a year or 2 in a traditional pond. And then you have to process, export, and ship it as carbonate. So there's a carbonation plant. And most important part is this takes time, it's expensive, and also polluting. So there is a need for environmentally friendly way, and some of the technologies are being considered and deployed. We'll talk about them. So what is the challenge? The lithium is not available in high concentrations. This shows dilute brines, about 5 different sites in USA, Salton Sea being highest lithium concentration. Still, too dilute is 200 parts per million, and all other sites are even less than that. Okay. So separation of multiple minerals is important, but they are also with lower value sodium, calcium, and chlorides. So you have a separation challenge, low concentration. You have to handle large amount of water that can cause environmental impact, as well as keeping the ecological balance is going to be very important. Particularly in USA, we have a lot of rules to keep safety of people, safety of the whole ecosystem. And so first way is separating by the diameter of ions, lithium, sodium, potassium. This shows their hydrated diameter. And you can see they are pretty similar. So it's very difficult to separate lithium from sodium and potassium, okay, using conventional membranes. So you need more selective membranes, and I'll talk about that. If you look at dehydrated diameter, then you see the differences, and it can lead to some potential innovative processes. And that is, what quite a few companies are looking at, and we'll talk about that next. So these are high-level technologies. emerging DLE technologies. One of them is adsorption, where selective adsorption of lithium ion or lithium compounds are taking place, and then you go through desorption to recover that. Same way, you can apply more selective ion exchange method, solvent extraction, or highly selective membranes. And more recently, electrochemical processes are being investigated. Ludwig and I, we spend our career mostly in electrochemical cells, and this system do provide unique advantages, but also there's quite a bit of work. Yeah. And at the end, you want to take out your salt lithium carbonate preferentially. So let's see where these processes stand. So this is similar technologies, adsorbent ion exchange and electrochemical separation. You can see the adsorbents are being used commercially. They do have adsorption, desorption step, sub-batch process, and that has a challenge of cost effectiveness, though more than 80% recovery has been demonstrated with a potential of going more than 90, as much as 99%. Ion exchange, solvent extraction, membranes, and those they use different materials to do the work, but they are all under development, what we call pre-commercial stage. Though they promise greater than 90% recovery of lithium. So let's look at some of them. So advanced membranes, it's very interesting to note that for the technology that Ludwig described on our membrane, waste heat to membrane power, what we are calling Pinakin cycle, okay, there are no major manufacturers in USA. And innovation in membranes is now in other countries. So this is very important low-hanging fruit. And which are the membranes? Reverse osmosis, nanofiltration, ceramic membrane. Fuel cells are based on ceramic membrane. For example, fuel cell energy and Bloom Energy, they lead in ceramic membrane manufacturing, particularly with electrochemical. Okay. So membrane area is very important part, but it has to be also in conjunction with other steps as shown here. And I'll explain this more. So where are the membrane pathways? Same membrane list on the left. What are the advantages? Reverse osmosis is the most proven. It gives you 50% to as much as 90% water recovery, which concentrates the lithium. And then, but because you have membrane fouling issue, the lithium recovery could be limited. So it's used as a pre-treatment. You concentrate to a certain level, then go through nanofiltration or ceramic or hybrid membranes. The last one is what we are projecting that has a bigger opportunity because it is running based on very little electricity. You have waste heat you are throwing away, less than 100 degrees C, you can drive forward osmosis. And that is the membrane module I'll explain to you. So when you look at improvement, obvious thing comes in is, can we use solar thermal? And this shows in the diagram, solar thermal array recovering the heat, and then lithium containing brine. First step is removing the monovalent, which is sodium, lithium compounds, and the divalents are removed there, and they have their own value. And then you go through purification of sodium chloride. So now you end up with lithium chloride. And that lithium chloride using the forward osmosis membrane concentrator. That's what Ludwig talked about earlier. The technology our team is working on, it can concentrate 2 to 10 times lithium, depending on how you run it. And it also provides high quality water as a byproduct. So this is benefits from super economizer technology as well as solar heat. Now, the waste heat driven, so you look at the solar, the lithium salts, brine, and using the module of advanced membrane. And as you saw earlier, lithium carbonate is the product. What is the unique is in the process, you are using heat, and that low level heat typically goes in a cooling tower. That heat now is a right input to produce electricity using super economizer and water turbine cycle that you saw earlier. So this is the unique WTV technology, the waste heat and the very dilute concentration, and now you can get electricity back. So basically it's making you more sustainable and more greater manufacturing efficiency, lower cost. Another applications after the solar thermal, you can convert with geothermal. So bottom half is the production well on the left-hand side where the hot brine comes out. And then the right-hand side, injection well, after separating lithium, you put everything back in the ground. So you are not changing anything, no environmental impact. You selectively took out lithium. How did you do that? Is the same cycle. You are using first waste heat driven advanced membrane, but then the leftover waste heat goes into our super economizer cycle. And that electricity you produce will support your lithium extraction process. So this is a win-win combination of high level heat available from geothermal, running a turbine, and then powering advanced membrane. And combination is a lower cost on lithium extraction. So we have looked at Goldman Sachs as an example. This company called Adsorption as a very unique technology. They have licensed this technology from Stanford University. It's a public information you can get from their website. So from multiple years in using conventional method, this technology shrinks that into days. Okay, and you can see left-hand side, the DLE modules, the brine from source is brought up, and then lithium chloride, everything gets converted, and that's where HCl, hydrochloric acid, is used. This is a very convenient way of all mineral extraction is get into chloride first, but there are two parts to it. You have a regeneration step where you make HCl, and you have to make sure that HCl doesn't end up in your discharge water. The technology that we talked about that provides water recovery for reuse. Another technology in the middle is lithium chloride conversion to lithium carbonate, which is the most favored in the batteries. And that has a potential to use CO2 in that reaction, and that makes carbon negative process. And that's another part of WTV. Okay. So where are they adsorption? They have shown in the lab greater than 99% lithium selectivity, which is excellent positive. Their efficiency numbers are greater than 90%. They have shown 500 cycles based on manganese-based solvents, and that lithium uptake about 10 ppm per gram of the sorbent. If this capacity can be increased, it can reduce cost sizably. Regeneration time also has been improved. Okay. It is versatile in varying concentration of lithium, and the use of CO2 makes the process carbon sink. So you are benefiting from what we call CO2 emissions. So the most important value is the lithium carbonate is directly compatible with market demand. It has been tested with oil field, geothermal sites, and smackover, and brines from USA, Canada, and Argentina. Where they are now, they have about a $2 million DOE contract to improve the sorbent robustness and have it more diverse, greater selectivity, eliminate use of hydrochloric acid, which is environmentally very, very attractive goal, and then CO2 integration and double the cycle life. Okay. And they are also looking at scaling up the sorbent manufacturing process, doing field testing, and commercial production facility design. So this is a very important step being taken by DOE. The seawater is the largest source of lithium, and for that reason, for all minerals, but they are extremely dilute, 0.2 parts per million. Okay. Sometimes even less, depending on where you are. So existing processes like precipitation, hybrid adsorption, they have extracted lithium from seawater. Okay. And newer membrane technologies can reduce the extraction cost. Most important part is reducing the capital cost and operating costs needed for commercial scale-up. Another technology is electrochemical. The diagram is shown on the right. Saudi Arabia is doing quite a bit of work in this area. And this uses electrochemical cell with a ceramic membrane. That's lithium lanthanum titanium oxide, LLTO. Okay. Co-products are lithium, chlorine, and hydrogen. And they have tested 0.18 ppm lithium and multiple cycles and concentrating that to 9,000 ppm. There is a control. Electricity consumption is an important factor. Today's electricity number is $5 per kilogram of lithium. That needs to be reduced. And robust membrane. University of Chicago has a parallel technology that uses iron phosphate, as particularly the lithium iron phosphate. This is a popular LFP battery electrodes or batteries that are good for stationary power. So it's a single step to battery material. Okay. What is required is they call olivine iron phosphate, and there's a design of its morphology, crystals. So what they have to do is make sure particle size, pore size, surface area, charge are properly controlled to get feedstock flexibility that is needed to operate on seawater. What is needed to be done is the scale up, improve the kinetics, and better selectivity of lithium over sodium. Stanford University has another third way of is using redox technology, electrodialysis, solid state electrolyte membrane shown on the right-hand side how it works. Lithium selectivity is pretty high. Most important benefit here is it reduces the energy cost by more than 90%. And that results in the lithium cost from $9,000 per ton to $4,000 per ton. Pretty impressive. Technology is modular, they have shown 4x scale up and reduce sizably the environmental footprint. The R&D challenges are they have to make membrane more robust and process scale up in a cost-effective way. So this technology has tested in the lab. It has to be tested with the real seawater. Very interesting thing is, as you saw, USA does not have any lithium production, but the awareness has resulted in Thacker Pass, Humboldt County, Nevada. This has the world's largest known reserve of lithium in USA. That means we have potential to become like oil production, world largest, Saudi Arabia type lithium production in USA. And there's an excellent project, public-private partnership, $3 billion investment with GM participating at $650 million. And we see our WTV technology has a good fit in that. That's the next slide. This shows they have phase 1, phase 2. Phase 1, they are going up to certain size and proving all components. And they are showing how the pre-treatment step, processing step will take place. And for leaching the lithium, they're using sulfuric acid. Now, sulfuric acid is very effective, but at the end, you have an acid neutralization. Okay, that requires additional steps, cost. And if you can recover, reuse acid, it's a great idea. The opportunity we see of waste heat is sulfuric acid reaction is very exothermic. And they are using some turbines to recover that heat, but low-level heat is planned to go to the cooling tower. This is where the our super economizer technology can improve its energy efficiency by additional 20%. So how do you see boosting the lithium supply chain? Okay, and with the emergence of DLE, and you can see this is a Bloomberg projections and different feedstock, different processes. And you can say, compared to where we were a couple of years ago, we are going to go through 5 to 10 times. Okay. Brine is expected to play a good role, DLE, but also there's a need to continue with the evaporative technology as well. So enhancing and accelerating the innovation of these technologies is definitely a good opportunity. Now, how does the DLE compare? And you can see in all the charts, carbon footprint, facility footprint, water consumption, capex, cost, and implementation time, all of them show DLE is very promising compared to today's feedstocks, hard rock and brine, solar evaporation. Yes. So with that, we'll take any questions you may have. Thank you.
Thank you so much, Pinakin and Ludwig, for your presentation. At this time, I encourage others to add questions to our Q&A box. Thank you for sharing more about your lithium extraction technologies and kind of how that fits into the scope of the U.S. lithium and critical material goals. While we wait for a moment for people to pop some questions into the Q&A box, I will share that this presentation will be recorded and available on YouTube after we finish with this. In about a week's time, you'll see it there on our Critical Material Innovation Hub YouTube channel. But to kick off our questions, while we wait for others to kind of put some into our Q&A box, Pinakin, would you mind elaborating a little bit more on how we can increase U.S. manufacturing, like competitiveness of our lithium extraction using some of these technologies that you guys were sharing, and kind of what you envision your technology is playing a role within our markets?
Yeah, thank you. That's a good question. Today's lithium extraction is mostly driven by China, and they have much more, relaxed rules compared to what we have here, and that brings the cost up. But having said that, it also gives us opportunity to look at how we can reduce that cost and improve our competitiveness. Is looking at wasted resource. The wastewater is a very big one, okay, number one. Number two, waste heat, cooling tower is equally big. Number three, CO2 that we are throwing away can be utilized for carbonation. Okay. Electricity, if you make it from wasted resources. So essentially you have 4 or 5 wasted resources. If you use it to make lithium extraction more economical, more environmentally friendly, now you can compete internationally with these technologies.
Thank you so much, Pinakin. We still have yet to see some questions pop into our Q&A box. So if you have some just on the tip of your tongue, or I guess your fingers, please type those into that box for us. We have kind of another moment. I will continue with my question and kind of ask where you see potential other critical material applications.
So the critical material, critical minerals, they are everywhere. In your cell phone, you have multiple materials. Okay, the electric cars that we drive, the batteries, they have not only lithium but a lot more other materials like nickel. Okay, the electric motors that is improving the efficiency. It contains pretty high performance magnetic materials. And at this time, bulk of these materials are not made in USA or not mined in USA. Over the last 20, 25 years or so, we have lost a lot of this ability to other countries. And now, for the national security reason and also economic reasons, it's important that these materials be mined from here, purified here, used here. And when you look at it, we are the major user of these materials. Defense-wise, there is equally similar situation. And so it makes a lot of sense to extract materials while we have all these resources available. And also, as Ludwig said earlier, we are throwing away 25 cords of waste heat. That waste heat is an excellent resource for purification at lower cost. So we need to change our thinking from do the work, low-level heat, throw away in a cooling tower, pay for throwing away, from that to extract this mineral. The other minerals processes work similarly as lithium. We just wanted to focus on lithium, but same processes can be used to separate other materials as well.
Thank you so much. You guys must have just covered all of the details within your presentation. If you guys do have future questions for Pinakin and Ludwig, their emails there on the screen, and please feel free to reach out. I'll have you guys move to the last slide for me, just so I can do a few closing pieces. Oh, we just got a question. All right, I'll let you guys take this.
Yeah, so I'll read the question. You mentioned about membrane production outside of the US, which may cause supply risks and bottlenecks. Is there an effort to produce membrane in the US? For evaluating the cost of new membrane being developed at a lower technology readiness level, what would be a good strategy to estimate the industrial scale production cost?
This is a very, very interesting question, very important one. We recognized this problem about 5 years ago when we were looking at our novel cycle, and we needed high pressure membranes. And we realized that USA has a very limited capability. And for good reasons, we wanted to get cheaper materials. So our technology went to other countries, and now they are making it. So there is certainly opportunity to look at the supply chain and bring it back. And I think CMI, this is a very good point, that membranes can give you very good quality lithium at lower cost, particularly waste heat-driven membrane separation. Okay, and the cost, we are working with some local supply chain and developing this, making it here. It's not an easy task because we have become used to getting good quality material from overseas. Okay, now we have to train our people, get the machines back to spin those membranes, in the right configuration, right specifications. So we are looking at those production costs and numbers. Please feel free to send us email with more details. I'll be happy to answer. But this is a very good opportunity.
Great, thank you so much for that response. I'll have you guys move to the last slide, unless there's any other questions that those have last minute. But as I wrap this up, please feel free to drop one last question if you have it. But this recording will be available in about a week's time, like I showed earlier, on aimslab.gov/CMI and on our Critical Materials Innovation Hub YouTube channel. I encourage you all to please join us in a month's time, or I guess a little less than a month, for our next webinar. That's going to be brought to us by Dr. Ruby Nguyen from Idaho National Labs. In the meantime, if you have some suggestions for future webinars, or if you have questions for our presenters, please feel free to reach out at cmi@minds.edu. And with that, I want to say thank you all for coming. Thank you, Pinakin and Ludwig, for your presentation and your insightful thoughts on lithium extraction.
Thank you so much.
Thank you.
Have a great rest of your day.
Bye-bye.